Alrighty, 1.3, let's get this one going. We're looking at geometric sequences now. We've started looking at arithmetic all the way through, but now we're going to look at geometric. What's the difference between the two? Well, let's start this way. All right, 1600 BC, the flood waters eventually subside. Or how about this one? Come on, Albert, hurry up and get to the part about multiplying. So that's going to give you a little bit of an indication about what geometric sequences are talking about. Arithmetic, that was talking about adding. We had a common difference between each term. In geometric, we're going to be multiplying to get to the next term. All right, get started. Oh, what's happening in these three? What's the rule? What's the next two terms? 1, 1/2, 1/3, 1/4, 1/5. Well, the next one in line there is going to be 1/6, 1/7. We're just going up by 1 on the denominator. 1/3, 1/9, 1/27. Hey, every one of those denominators is a power of 3. So the next power of 3, 1 out of 243, and 1, 729. 1, -3, 9, -27, 81. For each term, we're multiplying by -3. So 81 times -3, -243 times -3, 729. French pastry called, I'm not even going to try to say that one, is made of dough rolled into a square, buttered and then folded, baked into delicious yumminess. Ooh, I'm getting hungry just listen to this here. Okay, so you fold it into thirds, making 3 layers there. Repeat it as many times as you can until you can't do it anymore. We want to get to 1,000 layers. Get you started on this, but I want you to come up with the answer. So we start at the beginning, roll it into 1, and then we do our first fold. So we'll start with our first fold. So we'll say, oops, number of folds, or turns, because each turn is really 3 folds there. Okay. So if we do 1 turn, this being 1 turn, we've got number of layers is going to be 3. Now after the second one, we take that, roll it out, and fold it again. This time, the second turn that we do, you're going to have 3 from one side, 3 and 3 that are going to get folded in. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9 layers at that point. I want you to continue that pattern. When are you going to get to 1,000 layers? And just before we get into all of the lesson here, let's just make sure you know the lingo, the language that we're going to be talking about here. Powers and roots. Exponents are repeated multiplication. So really 5 to the 3 is 5 times 5 times 5. And again, the base is the number there. Our exponent is the number up there. And the whole thing together all of it is the power. And then just kind of reminding you that roots and powers, they go hand in hand. They're flip sides. So a cube root goes with cubing. Looks like that. So that if we want to find out, hey, what's r to the 5 equals 32, we're just going to do the opposite. And the opposite of doing the fifth is the fifth root of both sides. So then we would get r is equal to the fifth root of 32, which is 2. Now, as I mentioned for you, a geometric sequence is made by multiplying each term. And that's always by a constant. That constant is going to have a special name. That special name is the common ratio. Just like the common difference was for the arithmetic sequence, the common ratio is for a geometric sequence. And it's called a ratio because we find it by taking the ratio. In order to find a ratio, that means divide. T2 divided by T1. We're making a ratio between the two numbers. Or T3 divided by T2, as you can see along through here. But notice what we got. We got the common ratio is any non-zero real number. Ooh. Why? Why does it have to be a non-zero? And that's the question, the first question that you're going to ask that we're going to discuss, is why non-zero? And this is the whole reason why I teach and love mathematics. I get to act like a 3-year-old and always ask why. Next set of definitions that you got to be aware of. Infinite versus finite. Infinite means that it continues forever. Finite, on the other hand, means that it's going to stop. There's an ending point. How are we going to know? Well, if there's ... at the end. So right there, that's the key. Looking for the ... And then we can graph them. We can see, oh, look at that. Hey, they're going up, and they go on forever. This here is going to be called divergent, because they're not approaching a constant value. It's going up and up and up away from a certain number. It's really going to infinity. Now, if we look at this example here, you can see in the dots, they go back and forth and back and forth. Positive, negative, positive, negative, positive, negative. And it's not increasing nor decreasing because it's going back and forth between a positive and a negative. And this one is also divergent. So you're going to have to be able to identify, is a sequence, a geometric sequence, divergent or not? Well, let's look at one that is decreasing then. Means it's coming down. We can see that these points are going down, so they're decreasing. And if we notice, they're getting closer and closer and closer to a value of 0. They're converging. This is convergent. So it's either divergent, going away, not coming to a certain value, or convergent, approaching a constant value. And this is an important paragraph here. When we are given the first few terms of the sequence, we can't just assume that it's geometric, because it might look like it is. We have to be able to identify that, yes, there is this key thing, the common ratio. All right, let's start this first one. Find the 10th term of that. And is it convergent or is it divergent? So this is term 1, 2, 3, 4. That's fourth term. Well, in order to find the fifth term, we need to know what the common ratio is. Common ratio is made by T2 divided by T1, which gives us -3. Let's just check to make sure that it's also the common ratio by going 18 divided by -6. Yeah, that's -3 as well. We knew that because they told us it was a geometric sequence. As soon as they say it is, it is. So we could just go straight through and say, okay, 2, -6, 18, -54. All right, let's get to the next one. multiply it by negative 3. That's going to give us 162. And then do that again. Negative 486. Do it again. So we repeat it. We get all the way up to the 9th term. And now we do the final one again. Multiplied by negative 3. Which is going to give us the 10th term, which is now negative 39366. But wait, could we have done it a little bit easier instead of finding all the ones before the 10th term? Yeah, of course we could have. Let's look for patterns. That's what math's about. Find a pattern. Well, the first one was 2. The second one, we went 2 times the ratio of negative 3. Then the next one, we went 2 times the negative 3 times another negative 3, another ratio. Or in other words, 2 times negative 3 squared. This one was 2 times negative 3, one of them. Let's go to the next one. 2 times negative 3 times negative 3, and then multiply by another negative 3. Or in other words, we're doing 2 times negative 3 cubed. This first one was 2 times negative 3 with no negative 3's, an exponent of 0. Look carefully at the relationship between the term number, first term, and that exponent. Second term, the exponent. Third term, the exponent. Fourth term, the exponent. Well, what do you think 10th term is going to be? Hopefully you're able to see that pattern emerge right there, that it's going to be the original 2 multiplied by that ratio to the exponent of 1 less than 10, which is 9. Punch that into your calculator. You're going to see you're going to get the same answer. Some of those terms were positive, some of them were negative. What if I said term number 456? Is that going to be a positive or is that going to be a negative value? Put something down there. We'll discuss that. All right, let's create a term or a sequence now. The 6th term is 27. Okay, well, that means we've got term 1, 2, 3, 4, 5, 6. T6. That was 27. Well, let's now just figure out, hey, what do you want to use as our ratio, our R value? Pick anything. Let's pick something that nice and easily divides. Let's try 3. So that means to go back, just divide it by 3, or 9. Go back again, divided by 3. That gives us 3. Divided by 3 again, 1. Divided by 3 again, 1/3. Divided by 3 again, 1/9. Hey, perfect. There's a nice sequence. It's a sequence, so we got to make sure that we're putting a sequence and put those in there. Hey, let's make it infinite. I could have made it finite. I could have stopped at the 27, but I decided, hey, let's keep it going. Well, let's bring this knowledge together. Geometric sequence. The first term is T1. The second term is T1 times the ratio. Then we go multiply by the ratio again. And as I said, the term number is always 1 more than the exponent. Or the exponent is 1 less than the term number. Which gives us our formula, which is on your formula sheet. T1 times R to the n minus 1. All right, let's start this baby here. If in your work you take the square root of a number, you got to make sure you put plus or minus there. That means that there are two possibilities. We're going to have two possibilities for a sequence at that point. This is only going to happen with even exponents, never with the so even exponents, two possible R values. One positive, one negative. And also come up with something to discuss in this question as well here. All right, infinite sequence. There's T1, there's T5. Determine other values. Well, really, this question is asking us one thing. What's R? That's where we're starting with this. So let's label it out. T1, 2, 3, 4, 5, 6. Let's put in what we know. We know that T1 was 7, T5 was 567. All right, let's algebraically work this through here. What's happening is we're saying we got to multiply by R, by R, by R, by R. So in order to algebraically work, we're going to use our formula. Tn equals AR to the n minus 1. Let's look at T5. T5, we know, was 567. That's the value. We know what T1 is. Sorry, I'll put, sometimes they use A, sometimes T1. I better change that to T1 for you, because that's what's on your formula sheet. That T1 value, that's 7. Multiplied by R, I don't know what it is yet. That's what we're going to solve for. N, though, I do know that N is 5 in this situation. And hey, we can solve for R. So we've got 5, 6, 7 equals 7R to the 4. Hey, divide that 7 over. That gives us R to the 4 equals 81. And now we've got R to the 4. We're going to do the opposite of the 4, going to exponent of 4. That means 4th root. Oh, look at that. That's an even exponent. That means bump, bada, bum. We got two values, a positive and a negative. 4th root of 81, that's 3. So we've got plus and minus 3. Don't forget about the plus and minus. Star that for yourself. Give it a nice kiss on your page. Make sure that you remember that. So we're going to have two possibilities here. When R equals 3, let's do the work. If R equals 3, and we're looking for T6 and T2, then T6 is equal to T1, R to the n minus 1. T1 was 7 times R, which is 3, to the 6 minus 1. Or 7 times 3 to the 5, which equals 1701. But T6 could have also been negative 3. So let's do the work on that one. That means T6 would have been T1 R to n minus 1. T1 is still 7. R now is a negative 3. To the 6 minus 1, 7, negative 3 to the 5, negative 3 to the 5. That's going to give us a negative value multiplied by the 7. We're going to get the same value, 1701, but this time it's going to be negative. So then we've got to find T2 as well. Well, T2 would have been 7 times 3 to the 1. 7 times 3, hey, that's 21. And T2 over here would have been 7 times negative 3, 2 minus 1, or negative 21. The first term started positive. The second term, I don't know if it's going to be positive or negative. But the third term is going to be positive again, because either it goes positive, 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 or positive, negative, positive. The fifth term is also going to be positive. We don't know about the second term, the fourth term, and the sixth term. Are they going to be positive or negative? All right, let's apply it. We always like to end here with a written problem. StatsCan estimates the population growth of Canadian cities, provinces, and territories. Population Nunavut is expected to grow annually by 0.8%. In 2009, population was 30 grand. Estimate the population in each year to the nearest thousandth. 2013, what's it supposed to be? Always be careful with questions that are talking about percent, because that's not 0.8 as a decimal. That's 0.8 of a percent, which is actually 0.008. That's 0.8 out of 100 is what it's saying. So be careful with that right off the bat. That's where people are going to make probably the biggest mistake. Second thing, that's not the R value, because there's still 100% of the people that were there the year before. We're adding an extra 0.8%. So we've got 100% plus 0.8%, or in other words, 1 plus 0.008, which gives us our R value of 1.008. Right there's the first hard thing to do with a question like this. So term number 1. Term 1 is 2009. 2010. And that's the one we want. This is term 1, 2, 3, 4, 5. That's the second tricky thing of a question like this. You can't just say 2013 minus 2009 to get that we're talking about term 5. Because that 2013 minus 2009 is only 4. That's meaning there's 4 more terms than the first one. So if you're going to subtract, make sure you add the one back that you started on. Okay, so you can subtract, get 4 more than the first term that you started at. So term 1 was 30,000, and we need to get to here. So Tn equals T1 R to the n minus 1. Formula-based question, let's figure out what we've got. We've got Tn, that's what we're looking for. We've got T1, that's 30,000. We've got R, which we've just said is 1.008. And now we've got N, which we're telling us is 5. Let's plug her in and work it through. 30,000 times 1.008 to the 5 minus 1. Let's get her going. To the 4. Plug that into your calculator. And we get 30971.581. Nice. We've got 0.581 of a person. Oh, they told us to round to the nearest thousandth. Oh. So we need to go 31,000 about, approximately equal to. And let's repeat that, but this time at 2049. We don't want to draw lines all the way through, but we do want to remember that we can go 2049 minus 209, And that's going to give us 40. But we got to add on that extra starting place for the first one. So we're actually using an n value of 41. Plug her in again. So Tn equals 30,000, 1.008 to the 41 minus 1. This 40 here is actually talking about the 40 when you subtract it. So if you don't want to add 1, you can compensate by not subtracting 1 in the formula here. And this tells us that they should be about 41261.265. Again, quarter of a person sitting there. Nearest thousandth, that's approximately 41,000 people living in Nunavut. All right, last two things just to jot down something for yourself. Do some thinking here. Be prepared for discussion on these. How do you determine whether a given sequence is geometric? What assumptions you have to make? And what's going to happen if r is 1 or negative 1? All right, have a good one. See you in class.